Yesterday I left you with the problem of finding f of x plus h minus f of x all over h of this cubic function, 2x cubed plus 2x squared minus x. So I've shown you the expansion of this, substituting this is f of x plus h minus f of x all over h. You have to expand the cubic, expand the squared, distribute the negative, and then cancel out the common. There's a 2x cubed you can cancel out, a 2x squared you can cancel out, and a minus x and a plus x. So the last three, all of f of x can cancel out. And what you're left with is you have to distribute the 2 throughout the parentheses, distribute this 2 throughout the parentheses, and then don't forget about this little minus h at the end. So when you get done with that, you're left with this great big long polynomial. Each one of these terms has an h in it. So each one of those h's can be factored out, and then you can divide out the denominator. Oops, this denominator should have gone away. So you have 6x squared plus 6xh plus 2h squared plus 4x plus 2h minus 1 is your difference quotient result. And then if you substitute h equals 0, 3 of those terms go away and 3 of them stay. So there would be your final answer is h goes to 0. Well, why are we doing all of this difference quotient? Well, what we're doing is we're going to be introduced to a little bit of a calculus concept here. One branch of calculus is called differential calculus. Differential, T-I-A-L, differential calculus. And what you do in differential calculus, what it's all about is finding the rate of change of functions. Oops. So we're finding rates of change of functions. If you recall from Algebra 1, you found a rate of change for a linear function. For a linear function, back in Algebra 1, the rate of change is just the slope. So you can find the slope in y2 minus y1 over x2 minus x1. That's the slope of a linear function. So that's the slope of a linear function, and you can probably remember that pretty well. Well, in calculus, we're looking at mostly nonlinear functions. Nonlinear functions also kind of have a slope, if you want to kind of think about it in terms of how fast they change. So let's just take a look at just a kind of a regular nonlinear function. Well, what is the slope of this function? We'll call it f for f of x. Well, if you look at this part of the function down here, and if you tried to find a slope of that part of the function, what you do is you would draw a tangent line to it, and you'd find a slope of that tangent line. And the slope of this function down at this point would be 0. But then as you travel up the graph here, and if you stopped like part way up, and you drew a tangent line to this function here, you would see a slope of probably about positive 1. And then as you traveled up, the slope gets less and less and less and less, and finally when you reach the top of it and drew a tangent line across, you'd find the slope of 0 again. But then when you started heading downhill, and you stopped over here and drew a tangent line to this graph, well, this slope becomes negative. So for nonlinear functions, the slope is always changing. For nonlinear functions, slope is always changing. And it depends on what value of x you're at to figure out what the slope of it is. And so I've got a little diagram here of just a simple parabola. This is y equals a half x squared. And if you take a look at this point right here where x equals 1 and y equals a half, this slope looks like it's about positive 1. But then as you travel over onto the left-hand side of the parabola, and if you park yourself up at negative 2, 2, it looks like the slope of this line, this tangent line here, would be negative 2. Or if you traveled way up here, higher up, the higher up you get on the parabola, the steeper the line gets. You can see that this line is steeper than this line. So the rate of change here is greater than the rate of change here, although they're both positive. And this one is negative. And then this one is kind of part way in between the other two. If you park yourself at 2, 2, looks like the slope here is 2 instead of 1. So slopes change all of the time, depending where on the curve you are. And what our job is in calculus is to figure out exactly what that slope of the tangent line is at any point along that curve. So now what I'm going to do is I'm going to show you this worksheet that I handed you that says finding the slope of a tangent to a graph using the limit process. Well, limit processes are used all the time in calculus, and this is one of the most fundamental ways that it's used. So what we have here is just a plain old parabola. This is y equals x squared. And what we're going to do is we're going to figure out what the slope of y equals x squared is at this point down here called xy. Well, this point xy is 1, 1. And how you do this is you're going to find another point on this graph. You're going to connect these 2 points, and you're going to find the slope of this line right here. This line is called the secant. So the slope of the secant, what you're going to do is you're going to do a rise over run. So rise over run between this point 1, 1 and this point right here. This point is 4, 16. You can see that the slope has been calculated for you, 16 minus 1. Oops, we can put 1, 1 down here. All over 4 minus 1, and that slope is equal to 5. So the slope of this is approximation for the slope down here at 1, 1. The next thing we're going to do is we're going to move this point up here a little bit closer to the point xy. Xy is still 1, 1, because what we want to do is calculate the slope right here exactly at 1, 1. So we're going to slip on down here, and this point right here is 3, 9. The slope of this tangent line should be a little bit closer to the slope of this line down here. Well, the slope rise over run, 9 minus 1 over 3 minus 1. Well, this slope is equal to 4, which is a better approximation to the slope at 1, 1. And now we're going to slip down further, closer to this point 1, 1. This point here is 2, 4. And now we're going to calculate the slope of this secant line. Rise over run, this slope becomes 3. So you can see that the slope went from 5 to 4 to 3, and what we're doing is we're getting closer and closer and closer to the actual slope of the tangent line here at 1, 1. So if you turn over to the back of it, this point right here is 1.5, 2.25. And if you calculate the slope of this little point, it's probably pretty close to the slope of the tangent line here, which is what we want. And if you calculate the slope, it becomes 2.5. Looks like the slope is getting closer and closer to 2. Now what we have here is you can probably see that there's a difference quotient here, and that's what I want to explain is this difference quotient, and it's how it's used to find the slope of a particular tangent at a particular point. Well, this point here is called xy, and it doesn't matter what the point is. We just chose it to be 1, 1. And what we're doing is we're going over a certain amount, and this certain amount that we went over is called h. So the difference between this x point and this x point up here is h. And then we're going to rise up here, and this point right here, the y value, is called f of x plus h. So this x value right here is really x plus h. Now this h value is equal to 3 because we're going over 1, 2, 3 from the original. And this f of x plus h is really f of 4. but f of x plus h is equal to 16 here when we let h equal 3. Now we're going to step down here and we're going to let h, it says h equals 3 right here. Now we're going to go down here, and this point that becomes a little closer to 1, 1 is you're going over from 1, 1, you're going over 2. So this distance between this x value and this x value is 2. That's the h point. And then coming up here, f of x plus h, well, x plus h is 1 plus 2, which is 3. Remember, x is 1, y is 1. So x plus h is 1 plus 2, which is 3. And f of 3 is 9. The next thing we're going to do, or the next thing we did, was we moved this point a little bit closer to that point. So the xy value right here, this distance between this x point and this x point, this h value is equal to 1 because it's the distance between this x and this x. And this is also called f of x plus h, this y value right here. And in order to get a slope, y2 minus y1, well, y2 is f of x plus h. And y1 is just y. Well, you know y is f of x. So we've got y2 minus y1 over x2 minus x1. Well, x2 is x plus h, and x1, later. So we'll have x2, which is x plus h, minus x1, which is just x, and when you combine like terms, x plus h minus x just turns out to be h, because the x's cancel out. And like I said, this point called xy is really x, and y is the same thing as f of x. So the f of x plus h...
Please pardon this interruption. During this time...
Sorry for all of these interruptions today. Holy cow. Oh, so I'm just trying to explain that this is a slope, y2 minus y1, which is f of x plus h minus f of x, all over x2 minus x1, which is just x plus h over, or minus x, which just reduces down to h. So this difference quotient, I'll call it a dq, that's from yesterday. This difference quotient is just the same thing as the slope of the secant line. A secant line is just it's like a chord that connects 2 points in a nonlinear function. So the secant slope here turns out to be 5. Moving the point on down closer, the secant slope is equal to 4. Moving the point down closer, the secant slope is 3. Moving the point on closer, the secant slope turns out to be 2.5. So now what we really want to find is we want to find the exact slope of this tangent line right here. This tangent line would have a slope that's exactly correct if this little h value here is equal to 0. So right now, when I go over h, this h value is a half because I've gone over a half. But what I really want to do is I want to make h shrink down, 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 ever so small. So it's so infinitesimal that I really can't even tell that h has a value. It should be more like 0. So if I want to find the slope of this function f of x, I'll call it f of x, at point xy, and this point xy just happens to be 1, 1, but I'm telling you that at any point along here, x comma y, what we're doing is, like I said, we're trying to shrink this h down to 0. So this is a limit process. We're finding the limit as h gets closer and closer and closer to 0. We're shrinking that little delta x down here. And then we're just finding this slope function, which is f of x plus h This is y2 minus y1 over x2 minus x1, which just turns out to be h. This is a really, 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 really important formula in calculus. This is the difference quotient, but if you put a limit on the front of the difference quotient, you're finding the limit as h goes to 0. This is called the definition of the derivative of f of x. The derivative of f of x is the same thing as the rate of change at the point xy. So I guess I'll put that on my notebook here. Now, when I said one of the branches of calculus is called differential calculus, what it's all about, differential calculus, is finding derivatives. And a derivative, whoops, let me zoom in here. A derivative is a rate of change of a function. If it's linear, it's just a plain old slope. If it's nonlinear, the slope always changes, and you have to use the definition of the derivative on that. So that's why this whole f of x plus h minus f of x all over h is so important, because what we're doing is using the limit process. So h actually shrinks down to nothing, and we're trying to find the exact slope of this function at h is equal to 0. So what we're going to do in tomorrow's class is we're going to use the definition of this derivative here. I'm going to ask you to find derivatives of various functions like f of x equals x squared. And that's pretty much the same thing as that whole worksheet that you did in class on finding the difference quotient for many different functions. But then what we're going to do is we're going to actually substitute the value of x in to the final answer that we got. Like over here on the day before the video, the day before, we always found an answer when h is equal to 0. And we can substitute a specific value of x into these third column function values to find the actual slope or the actual derivative of these given functions over here. This is the function in the left-hand column. When h is equal to 0, this is called the derivative over in this right-hand column. And I think that's about it for today with all the interruptions.